In this presentation, I'll be explaining AC voltage controllers, that is AC to AC converter, and the control technique used is phase angle control. Now let us the phase control single phase AC controller with resistive load, that is R load. And this is the circuit topology in which the input is a single phase AC supply equal root 2 Vs sin omega t or Vm sin omega t is the input voltage, and this is the load, and between them there is a two SCR, they are connected in anti-parallel, that is T1 and T2, and during the positive half cycle of the input T1 can conduct, and during the negative half cycle of the input T2 can conduct. And here the waveform for the single phase AC full wave voltage controller with resistive load is shown here, and see that one, this is the input voltage, that is the voltage at this point with respect to this, that is shown here. The input voltage is shown here, and here the since it is a phase angle control, the firing angle can be controlled here. For example, this is the firing angle for the T1, and this is the firing signal, so the gating signal for the T2. Therefore, this is the gating signal for T1, and this is the gating signal for the T2, and this is the input voltage, that is the voltage at this point with respect to this. And when during the positive half cycle, that is 0 to pi radians, T1 can conduct because that is getting forward bias. Therefore, once the firing angle comes, firing gating signal is coming certain angle, firing angle alpha, then this will be conducting, and the output voltage will be same as the input voltage. That is why at the firing angle alpha, you'll be getting the same voltage as the input. And once the current through this one, because this is a current waveform, which will be, since it is a resistive load, this current will be in phase to the voltage. Whatever the voltage, this one, that divided by the resistance will give the current. And once the current through the device or the SCR is going less than the holding current, that device gets turned off. Therefore, at this point, since the current is going zero value, this SCR, which is already in conduction, that is T1, that gets turned off. And the next firing pulse, that will be gating signal, is coming only at the instant pi plus alpha radians. Therefore, at this instant only happens. And during that negative half cycle of the input, this is getting forward bias because this plus is, and this is with respect to this one, this is plus. Therefore, this can be triggered, or T2 can be triggered at an angle pi plus alpha. Therefore, that will be conducting during that period, and at that the corresponding voltage here of voltage of this one with respect to this one, they will be getting as the same as this one, where negative voltage comes here. Again, once the current goes through this, T2 is going less than the holding current, that gets the SCR gets turned off. So that's a natural commutation or line commutation that gets turned off. Now that output voltage will be zero until the next firing. Therefore, you can see that one, until the alpha, the output voltage is zero. Then the output is same, voltage is same as the input. Again, that is zero until the next pi plus alpha. Then same as the input voltage from until 2 pi. Then 2 pi plus until 2 pi to 2 pi plus alpha. Again, the voltage is zero. Therefore, this is the voltage waveform, and the corresponding current waveform, which is in phase to the voltage, because we are considering a resistive load. Therefore, these two are the voltage across the thyristors T1 and T2. That can be obtained by the input voltage minus this voltage. Load voltage will give the voltage across the thyristor. Therefore, that is the thyristor voltage T1, as well as this is the voltage across the T2. Therefore, these are the waveforms for the single phase AC full wave voltage controller with resistive power. This is this control technique called the phase angle control. We are controlling the firing angle or the phase angle, and will be varying the RMS value of the output voltage. Therefore, this is the output voltage, and the RMS value of this output voltage can be changed by changing the firing angle alpha. We'll be deriving the equation for the RMS value of this output voltage in terms of the firing angle. And the output voltage and the current waveforms are the half, because this is the output voltage and this is the output current or load current. And this has got a property, what we call it as half-wave symmetry. Half-wave symmetry means that Ft equal to Ft plus T of minus, or minus Ft plus T. That is that is the value of the function at any instant T equal to minus of Ft plus T by 2. That property is there, this waveform. That is why this has got a half-wave symmetry. If this has got a half-wave symmetry, if you do the Fourier analysis, the corresponding constants like Ft equal to A naught plus sigma n to 1 to infinity n cos n omega t plus bn sin omega t. In that one, the constant A naught corresponds to the DC component, or this is the average value of this one. Since both halves are equal, average value equal to 0, or we can say that the constant A naught will become 0. It is the DC value or average value of the waveform. That is equal to 0. Next, AN and BN can be derived, and that will be seeing in the, that is for a half wave symmetry, we'll be seeing what is AN and what is BN, and we'll be deriving that equation in the coming slides. So this has got a property of the half wave symmetry. Therefore, in that case, A naught equal to 0, and this is the, in that equation, that is Fourier equation is ft equal to A naught plus sigma 1 to infinity an cos n omega t plus bn sin omega t. If we had got a half wave symmetry, A naught will become 0, and we'll be deriving the equation what is An and Bn will be present. That we can see that only odd harmonic will be present. We'll be seeing the next slide. What is the An and what is the Bn? What are the different frequency components in this one can be derived in the coming slides. Now let us derive the what is the RMS value of the output voltage. That is, this we have to find out the RMS value of this voltage. RMS value of the output voltage. The output voltage, the voltage equation for this waveform is given by root 2 Vs or sin omega t or Vm sin omega t. And the RMS value, root mean square value, means it is equal to 1 by pi integral, that is alpha to pi Vm square sin square omega t d omega t, and that is to be divided over pi or 1 by pi, and that is under square root to the half. Therefore, under square root 1 by pi integral alpha to pi Vm square sin square omega t is the RMS value of this voltage. Or if you derive this one here, 1 under square root 1 by pi integral alpha to pi Vm square sin square omega t equal to 1 minus cos 2 omega t divided by 2 d omega t. And that again Vm will be taking outside, Vm divided by root 2, then under square root 1 by pi integral alpha 2 pi 1 minus cos 2 omega t d omega t. Now we can see that one Vm by root 2 into, if you integrate this one and substitute the limits to the alpha 2 pi, the equation will become Vm by root 2 into square root of 1 minus alpha by pi plus sin 2 alpha divided by 2 pi. Therefore, this is the equation of the RMS value of this output voltage. Root mean square value of the output voltage is given by Vm by root 2, that's the maximum value of this voltage, divided by root 2 into square root of 1 minus alpha by pi plus sin 2 alpha divided by pi, where alpha is the firing angle. That means that as alpha changes, the RMS value of the output voltage will be changing. Or by controlling the firing angle, you can vary the RMS value of the output voltage. Now, if you substitute here, or the V0, the output RMS value of the output voltage can be varied from, if for example, if alpha equal to say 0, you'll be getting it is equal to Vm by root 2. If alpha equal to 0, it is equal to Vm by root 2. Now, if alpha equal to say pi, you'll be getting 0 output voltage. Therefore, it can be varied by changing the firing angle. You can vary the RMS value of the output voltage as per this equation, Vm by root 2 into square root of 1 minus alpha by pi plus sin 2 alpha by 2 pi. As an example, say alpha equal to pi by 2. If you substitute alpha equal to pi by 2 in this equation, we'll see that one, it is the corresponding RMS value equal to Vm by 2. Therefore, if you make the firing angle equal to say pi by 2 or 90 degree, the RMS value of the output voltage is equal to Vm by 2. If firing angle equal to 0, it is equal to Vm by root 2. Like that one, by changing the firing angle of this phase angle, okay, it's firing angle or it's called the phase angle. By changing the firing angle or phase angle of this controller, you can vary the RMS value of the output voltage. That is it's called the phase control. Now let us derive the power factor. How does this affect the power? Because the output voltage is this one. It is, it's not purely sinusoidal. There are harmonics are there. Apart from the fundamental harmonics are there. If you do the analysis, we'll see that later. Therefore, that will be causing a reduction of input power factor. We are going to derive what is the input power factor. In order to find out the input power factor, the basic concept is that input power factor equal to what is the active power, what is the power consumed by the load, that's called the active power, that divided by the apparent power, that is volt ampere. That ratio we call it as input power factor. Then active power means that power output divided by VA. Output power is in that RMS value of this voltage into the RMS value of the current. That is the power output. The power consumed by the load equal to RMS value of the output voltage into the RMS value of the current. Of course, in this case, the that is the here V0 already we derived as active power. In this case, actually here since we are using a resistive load, I mean here V0 and I0 we are taking as the power output, and the V and the corresponding V apparent power means that what is the RMS value of the input voltage and in what is the RMS value of the input current. Therefore, Vs into Is. But we can see that one RMS value of the load current is same as the RMS value of the source current. Therefore, I0 equal to Is, that it gets cancelled, or the input power factor is given by RMS value of the output voltage divided by the RMS value of the input voltage. Therefore, that is equal to the RMS value of the output voltage divided by RMS value of the input voltage is equal to Vm divided by root 2, or root 2 V0 divided by Vm. And we are going to substitute already we have derived what is the RMS value of the output voltage in the previous slide. It's not. Therefore, that V0 is being substituted here, or Vm by root 2 into square root of 1 minus alpha by pi plus sine 2 alpha by 2 pi. This is the RMS value of this output voltage, that divided by the maximum value into root 2, or if you substitute here, it will be getting square root of 1 minus alpha by pi plus sine 2 alpha divided by 2 pi, or this is the power factor at the input side. That is, as alpha changes, as the firing angle changes, we can see that the power factor is changing. For an example, if you make alpha equal to pi by 2, or if this is alpha firing angle is equal to 90 degree, in that case, if you substitute here 1 minus pi by 2 divided by pi plus sine 2 pi by 2 divided by 2 pi under square root, we'll be getting it is equal to 1 by root 2, or 0.707. Therefore, the power factor corresponding to a firing angle of, or a phase angle of pi by 2 here, the 0.707. Or if alpha is more here, power factor gets reduced. Anyway, as the firing or the phase angle changes, of course, the magnitude of the RMS value of the output voltage changes as per this equation. I mean, as per already we have derived that equation, this one, as per this equation, the RMS value of the output voltage is changing. At the same time, the input power factor is also changing as per this equation. Square root of 1 minus alpha by pi plus sine 2 alpha divided by 2 pi. Therefore, for alpha equal to pi by 2, it is equal to 0.707. The power factor, the input side equal to 0.707. Therefore, these are that's the input voltage, and this is a gating signal for T1, T2, and this is the output voltage, and this is the output current. We are assuming that it's a resistive load, and here this is the voltage across T1, and this is the voltage across T2. Now let us see the harmonic analysis of the output voltage. We have seen this is the output voltage already. We have explained that one. From alpha to pi, it is same as the input voltage. From pi to pi plus alpha, output voltage equal to 0. Again, pi plus alpha to 2 pi, it is same as the input voltage. From 2 pi to 2 pi plus alpha, again 0. That is repeating. Therefore, this is the shape of the output voltage, and corresponding current is, of course, if you are assuming a resistive load, it will be in phase to the voltage, and this is the corresponding current through the load. This is the corresponding current through the load, and this is the voltage across the load. Now we have to do what are the different frequency components. If you do the Fourier analysis of this waveform, apart from the fundamental, of course, DC component is 0, because average value, if you take this area equal to this area, positive area equal to negative area, for the average value equal to 0, that is why the constant A0 equal to 0. In that Fourier, constant A0 will be 0. But we have to derive what is AN as per this equation, what is the AN and what is BN. For AN is equal to the Fourier constant AN equal to, and we can see that output voltage, if you do the Fourier analysis of this one, it is equal to AN sin n omega t plus BN sin omega t. Of course, here n is changing only for the odd quantity will be available, because it has got a property of the half-wave symmetry is there. We'll see that one, only the first harmonic, third harmonic, fifth harmonic, only odd harmonics percent. And similarly here also odd harmonics percent. Therefore, the output voltage equation can be written as sigma 1, 3, 5, 7, etc. up to infinity, AN sin n omega t plus 1, 2, 3, 5, sigma 1, 2, 3, 5, etc. up to infinity, Bn sin n omega t. For n that is corresponding to 1, we call it as fundamental. Corresponding to 3, we call it a third harmonic, like that one. Therefore, if you calculate corresponding AN can be calculated. AN equal to, since it is having a half-wave symmetry, here ft equal to minus of ft plus t by 2, ft equal to minus of ft plus t by 2. Since it is half-wave symmetry, an can be written as 2 by pi integral 0 to, sorry, alpha to pi, not 0 to pi, alpha to pi, of course here b0 omega t sine omega t d omega t. Therefore, similarly b0 equal to 2 by pi integral alpha to pi b0 omega t sine n omega t d omega t. We have to integrate this one, and we'll be seeing what is the result of the coming slides. Therefore, this is the an and this is the bn, and this is the output voltage. Different frequency component can be obtained by substituting the value of the this n 1, 3, 5, etc. Odd harmonic will be present. And again, we can see that one, the DC component equal to 0. Therefore, the output voltage and the current waveforms have half-wave symmetry, and there's no DC component. That is why A naught equal to 0. And this is AN and this is BN. So, this is the circuit topology as already we have discussed. As we have seen, the equation for AN already we have seen in the previous slide. And if you substitute in that one, 2 Vm by pi integral alpha 2 pi sine omega t sine n omega t d omega t, and if you substitute in this equation, you can see that one, it is equal to Vm by pi sine n plus 1 alpha divided by n plus 1 minus sine n minus 1 alpha divided by n minus 1. Therefore, this is the equation for the AN, and similarly Bn can be derived 2 Vm by pi integral alpha 2 pi sine omega t cos n omega t d omega t, which is equal to Vm by pi alpha 2 pi sine n plus 1 omega t minus sine n minus 1 omega t d omega t. And if you integrate this one and substituting this limit alpha and pi, it is equal to Vm by pi cos n plus 1 into alpha minus 1 divided by n plus 1 cos n minus 1 into alpha minus 1 divided by n minus 1. Therefore, this is the equation for Bn, and this is the equation for An, or the Fourier constant An and Bn for this output voltage waveform. Now we'll be seeing what is the fundamental as well as the different harmonic component magnitude in the coming slides. Therefore, we see that one in the coming slides. Therefore, in the previous slide, we have seen what is An and what is Bn, and then what is the maximum value of the nth harmonic is given by, square root of An square plus Bn square, and corresponding phase shift equal to tan inverse Bn by An. Therefore, this is the equations to find out the maximum value of the nth harmonic. You'll be calculating what is An, what is Bn. Square root of An plus Bn square is equal to maximum value of the nth harmonic. And in order to find out RMS value, you have to divide by root 2. Then we'll be getting the RMS value of the nth harmonic. Similarly, the phase shift is equal to tan inverse Bn by An. Now, for example, if you are calculating the corresponding maximum value of the fundamental, you put n equal to 1. If you put n equal to 1, corresponding constants are A1 and B1. In that equation, we can get A1 and B1. A1 equal to, again the same equation, 2 by pi integral alpha 2 pi Vm sine square omega t d omega t. Then we'll be getting Vm by pi into sine 2 alpha divided by 2 plus pi minus alpha. Therefore, this is the constant, Fourier constant for the fundamental A1. Again, the Fourier another constant B1 for the fundamental 2 by pi integral alpha 2 pi Vm sin omega t cos omega t d omega t, or Vm by pi into cos 2 alpha minus 1 by 2. You are getting what is the A1 and what is B1. Then the fundamental maximum value is given by square root of A1 square plus B1 square. That is the maximum value of the fundamental. Of course, its RMS value equal to that maximum value divided by root 2. Now continuing harmonic analysis of voltage, the maximum value of the fundamental as we have seen is equal to square root of A1 square plus B1 square. We will be substituting what is A1 and what is B1 from the previous calculated value. For this is A1 that square plus B1 square under square root. That is the maximum value of the fundamental. That is Vm by pi into square root of sine 2 alpha divided by 2 plus pi minus alpha whole square plus cos 2 alpha minus 1 or 2 divided by 2 whole square. All will be getting, and the corresponding phase angle shift for the fundamental is given by tan inverse B1 by A1. Tan inverse cos 2 alpha minus 1 divided by sine 2 alpha plus sine 2 into pi minus alpha. Therefore, this is the phase shift for the fundamental, and the maximum value of the fundamental is given by this one. Therefore, the maximum value of the fundamental is given by square root of A1 plus V1 square, and that we are derived, it is equal to this one. And similarly, the phase shift of this one is given by the corresponding phase shift. Phi 1 is given by, that is, what is the phase shift of the fundamental? That is phi 1 equal to tan inverse V1 by A1. This is the phase shift for the fundamental, and this is the maximum value of the fundamental. And of course, the RMS value of the fundamental equal to maximum value of the fundamental divided by root 2. Next, we are going to consider the again phase control single phase AC controller with RL load. Instead of a pure resistive load, we are considering an RL load. And the same circuit, there are two thyristors, T1 and T2, they are connected in anti-parallel. This is the input voltage is there. Therefore, the input voltage is here. This is a gate impulse for T1 and this is a gate impulse for T2. Here, the difference is that, even, for example, in this case, the input voltage is going negative after this pi radians. But because of this inductance, the inductive energy will be there. Because of this inductance, even though the current is not going zero here, you can see that one, because of the voltage across the inductor, that is energy stored in the inductor, due to that one, even though the input voltage is going negative, because of this voltage across the inductor, this is getting forward bias, but is already conducting SCR, no, that is again continuing to conduct because that is getting forward bias. And of course, because of this energy, that the current is, after that one, you can say that one, that is discharging, or the current is decaying. After zero crossing, current is decaying, and once the current through this one or is reach until that point, the output voltage of this across the load is same as the input voltage. That is why you can see that one at this from the instant here, the output voltage here. We can see the output voltage here same from this one firing angle. It is fired, and the output voltage is coming here until the current is going to zero. You'll be getting the same as the input voltage. Once the current through this thyristor is going zero here, the device is getting turned off. And next triggering of next thyristor T2 is happening only from at the pi plus alpha. Therefore, from this instant we call beta here. From beta to pi plus alpha, none of the SCR is conducting. That is why output voltage equal to zero. Therefore, from beta to pi plus alpha, the output voltage equal to zero. Again, from pi plus alpha, T2 is triggered. That is, T2 is triggered. Then again, when T2 is triggered, the output voltage is same as this voltage. What is the same as the input voltage? You are getting the input voltage. Here also, even though at this instant the voltage polarity is changing to positive value, still this thyristor is conducting. That is because of the inductive energy. Because of this voltage across the inductor, still this device is getting forward bias, and that continues to conduct until the current through the device T2, that is the current through the D2, that is reducing to zero, that continues to conduct. Therefore, that until this point. Again, until the next triggering of this T1, none of the thyristor is conducting, the output voltage equal to zero. Therefore, this is the output voltage waveform. Because of the inductance, the RL load, this is the output voltage waveform, and this is the corresponding current waveform. This is discontinuity is there. For example, from beta to pi plus alpha, zero current. Again, from this point to this point, here there is a current, discontinuity is there. Pi plus beta to, again, here to pi plus alpha, etc. Here the discontinuity of the, during that period, the output voltage equal to zero. Therefore, this is the output voltage waveform, and these are the voltages across the thyristors T1 and T2. Now, continuing the phase angle control, AC voltage control with a RL load, as we already seen in the last slide. The corresponding equation governing, that is, when T1 is conducting, the corresponding we have to apply the Kirchhoff's voltage law to this loop. Therefore, Ri plus L di by dt equal to Vm sin omega t. And we have to solve what is the equation, but that is derived this current equation. We have to derive the equation during the conduction of T1 thyristor. And this is the Kirchhoff's voltage law equation, and we have to solve this first order differential equation, and we'll be getting it is equal to Vm by Z sin omega t minus 5 plus a constant K1 into e raised to minus R by L into t. Therefore, this is where Z equal to the impedance R square plus omega square L square, and phi equal to the phase shift equal to tan inverse omega L divided by R in this equation. Therefore, this is the current equation in which we have to find out what is the constant K1. In order to find out the constant K1 at omega t equal to alpha, we can say that at omega t equal to alpha, the corresponding current equal to zero. Substituting this one in this equation, we'll be getting what is the constant K1, like minus sine alpha minus phi into e raised to R by L into, of course, it is equal to L into of course, alpha into omega. Therefore, you have to substitute this alpha here and you have to equate to this current equal to 0. From that one, you can find out what is the constant K1. And that constant is substituted in the equation. Therefore, you'll be getting the final equation of this current. That is when the T1 is conducting, the corresponding current equation is governed by this equation. Of course, the solution is this one. The current solution is this one. That is given as the current through the, of course, through the load when thyristor T1 is conducting. Again, this is, we have seen the current equation of this one. And again, when IT equals 0, that is decaying, the current is decaying to 0 at angle beta. So this is called extinction angle beta. That can also be found out by solving this equation, that is at T equal to B, at omega T equal to beta or T equal to beta by omega, substitute this equal to 0, then you'll be getting what is this. From this equation, you'll be getting sine beta minus alpha phi equal to sine alpha minus phi d raised to minus R by L into alpha minus beta divided by omega. And from this equation, we can solve this extinction angle beta. Beta can be obtained from the above equation by once you get beta here, the conduction angle, that is gamma equal to beta minus alpha. That is the period during which it is conducting. That is conduction angle is given by beta minus alpha. So this is the way how much we can calculate this conduction angle and the extinction angle. In order to calculate the RMS value of the output voltage, that is this output voltage of this one, RMS value, it is equal to square root of 1 by pi. This is changing from alpha to, this is equal to beta. This angle is equal to beta. Therefore, alpha to beta, Vm square sine square omega t d omega t. We have to solve this equation and we'll be getting it is equal to Vm by root pi square root of beta minus alpha plus sine 2 alpha divided by 2 minus sine 2 beta by 2. Therefore, in terms of alpha and the institution, that is beta, you will be getting the RMS value of the output voltage. That depends upon the value of the inductance. If this beta value decides by the value of the inductance. Now continuing the phase control phase AC voltage control with the RL load, same circuit here. Now the two terms to be defined. One we call it as, we've seen that firing angle, that is firing angle of these thyristors T1 and T2. Second factor to be considered is what is the power factor of the load. Power factor of the load, that is RL load, what is the power factor? Phi is the power factor angle of the, this load as such. Now here, this is the, we can see that this is the input voltage and this is the input current as such. Therefore, this angle, the power factor angle, we are taking that this is a power factor angle phi. Now, if the firing angle is equal to the power factor angle, the three cases comes when firing angle equal to, or when it is less than, or it is more than. The three cases comes. First case, we are considering that if the power factor angle or the firing angle is same as the power factor angle. That is, in that case, from 0 to 5, T2 conducts, and from 5 to pi plus alpha, T1 will be conducting. That is, from 0 to 5, you can see that one, the current is negative. Since the current is negative, means that can conduct by only these thyristors. T2 will be conducting. And from 5 to pi plus 5, since it is the current is positive, T1 will be conducting. So from 0 to pi, T2 will be conducting. From 5 to pi plus 5, T1 will be conducting. Again from pi plus 5 to 2 pi plus 5, you can say pi plus 5 to 2 pi plus 5, you can say the current is negative. Then T2 will be conducting, T2 conducts, and so on. Therefore, this is the process which the devices that are conducting is decided by the what is the power factor angle and what is the firing angle. If you are selecting the firing angle same as the power factor angle, These are the devices which will be conducting depending upon the polarity of the current. If current polarity is negative, T2 will be conducting. If the current polarity is positive, T1 will be conducting. So let us see the second case. The firing angle is less than the power factor angle. You are firing an instant before this is the power factor angle. If you are firing before this, power factor angle, what is happening that one? Because here, if the alpha is decreased below 5, when T1 is triggered, when if you are triggering the T1 at an alpha which is less than the power factor angle 5, T1 will not get turned on, because since the current is negative, T2 is conducting. And since T2 is conducting, the drop across T2, here plus and here minus, that will be reversing biasing the T1. Therefore, we cannot trigger this T1 until it reaches to the zero current of this T2. Therefore, here, because of that, T1 will not get turned on because it is reverse biased by the voltage drop in T2, which is already in conduction. And the T1 will get turned on only at 5. Only at 5, even though you are selecting an alpha less than 5, that gets turned on only at 5 when the current through the T2 is going 0. Now T1 conducts from 5 to 5 plus 5, 5 plus 5. Therefore, that is the case when the firing angle is less than the power factor angle 5. But if T2 is triggered at an angle pi plus alpha, which is less than pi plus 5, as because positive current is there, therefore T1 is conducting, that the drop across T1 reverse biases the T2. A voltage drop in T1 will apply a reverse bias across T2. As a result, T2 will not get turned on or at pi plus or on at pi plus alpha, but only at pi plus 5 when IT1 equals 0. This is the triggering of the T2 happens that way. Now T2 will conduct from pi plus 5 to 2 pi plus 5. This is the case when the firing angle alpha is less than the power factor angle 5. Therefore, if the firing angle is less than the power factor angle, reduction of alpha below 5 is not able to control the load voltage and load current. That is the one observation. If you are selecting a firing angle which is less than the power factor angle, you cannot have a control, not be able to control the load voltage and load current. And thus AC output voltage can be controlled only for a firing angle more than 5. Therefore, depending upon the power factor, you can select a firing angle which is more than the power factor angle. That is, the control is possible only for the firing angle more than the power factor angle. That is, control range of the firing angle is between 5 power factor angle and 180. This is only the control range possible here. Therefore, that is the case when an RL load is connected. That is, it is not the case in the pure resistive load, but in an RL load, this is a constraint is that you can have a control of the this AC voltage control that is possible only for the firing angle, which is more than the power factor angle, and in between power factor angle and 180 degree, we can have a control of the output voltage. Therefore, that is the effect of power factor of the load and its control angles.